If we have one switch, then we can implement two combinations, and if we have two switches, we can implement four combinations. This is something we already know, and I can generalize this. If I have m number of switches and n is the total number of combinations that we want, then 2 to the power m is equal to n, right? Or I can write m equals to log with base 2 n. So if we know the number of combinations, we can easily find out the number of switches required. For example, if n is equal to 8 is total number of combinations, then m is equal to log base 2 8. We can write 8 as 2 to the power 3. Then we have 3 log with base 2 2, and this is equal to 1, so we have 3. M is equal to 3. We will use 3 switches to implement 8 combinations. Now if I consider a switch and a bulb, and they are arranged in this manner. This is switch, let's call this switch A, and we have a bulb here. This is the bulb, and if I apply voltage V, and this bulb is our output, let's call it Y. When this bulb is on, I will consider output to be 1. When this bulb is off, I will consider output to be 0. In the same way, if this switch A is closed, I will consider it 1. So we can have a table. A is the input, Y is the output. When A is 0, it means when A is off, it is opened, then definitely the bulb will be off, so Y is going to be 0. In the same way, if A is 1, on, it is closed, then we have a generous flow of current through this bulb and it will glow. It means output is going to be 1. So this is simple series arrangement for the switch and bulb. Now I want to change the condition slightly. We will have a new table. When A is low, the output is going to be high. When A is high, the output is going to be low. And we will have a new circuit that will be parallel circuit. Okay, we will have the bulb as our output, and now we will have a new position for our switch. The switch will now be connected like this. This is A, our switch, and this is the potential difference that we are applying. And you can clearly see when this switch is opened, it means 0. The current will flow like this, and there is a flow of current through the bulb, that's why it will glow, and output is 1. And if we make this switch closed, then current will flow like this, and there is no current through this bulb, and the output is going to be 0. So we have a parallel circuit like this, and now we are going to discuss the AND operation. We will now discuss the AND operation. We will take two switches, A, B, Y is the output, bulb. We have four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Now most of you already know what is AND operation, what we have to do in case of AND operation. The output Y will be high only when both the inputs are high. So it means for the first case, both the inputs are low, so output is going to be low. For the second case, A is low, B is high, output is going to be low. For the third case, A is high, B is low. It means output will remain low again. And for the final case, when both A and B are high, the output is going to be high. Now we will try to obtain the circuit for this AND operation. We have two switches, A, B, and the output is bulb, This is the output Y. You can clearly see when both A and B are opened, no current will flow through the bulb. When A is open, B is closed, then also no current will flow. And when A is closed, B is open, then also no current will flow through the bulb. And finally, when both of them are closed, then only there will be a current through the bulb and it will glow. So this is a simple circuit for the AND operation. Now we will move to the OR operation. A, B, Y, 0 0 0 1 1 0 1 1. In case of OR operation, the output will be high if one or more inputs are high. In first case, both inputs are low, so Y is going to be low. In the second case, B is high, so Y is high. In the third case, A is high, so Y is high. And finally, both of the inputs are high, so the output is high. Now we'll try to obtain the circuit for the OR operation. This is our first switch, A. This is B, the second switch. And we will have the bulb acting as the output. When both A and B are opened, there will be no current through the bulb, so output is going to be 0. When A is open and B is closed, the current will flow like this. So there is a flow of current through the bulb and hence output is high. In the same way, if A is closed and B is opened, the current will flow like this, and thus the output is 1. And when both A and B are closed, then also the current will flow through the bulb and output is going to be high. The next operation is NAND operation, and you already know NAND operation is Y equals to A and B and its complement. We have to take the complement of AND to obtain the NAND. One very important thing that we have skipped is this parallel circuit is nothing but the NOT circuit, right? We have taken the complement of the input. A was 0 and the output is 1. The complement of 0 is 1. In the same way, when A is 1, its complement is 0. So this circuit is the NOT circuit, and we want the NAND operation. So the truth table will look something like this. Y equals to A and B complement 0 0 0 1 1 0 1 1. We have to just take the complement of these outputs from the AND gate. So we will have 1 1 1 0, and you can see in the initial two circuits, the first one was series, the second one is parallel or NOT. And to obtain the NOT, what changes we have done? We have put this switch to the new position that you can see. So to obtain the NOT of a circuit, we have to change the position of switch like this. So the same thing we are going to do with the circuit of AND gate. We have this circuit of AND gate. This is the circuit for AND operation. The output is Y, and to obtain the NAND, we have to remove this switch from this position, and we have to put the two switches like this. The same thing we have done in this case. We have removed this switch and put it like this to obtain the complement, and to obtain the NAND from AND, we have removed this switch from this position and put it like this. Or you can easily find out this circuit from this table, but it is just a simple trick to remember how to obtain the complement of any given circuit. Now we will move to the next operation, that is NOR operation, and you all must have the idea how to obtain the NOR operation. It is the complement of OR, and we have the table like this. We have to take the complement of the outputs from the OR table 0 1 1 1, so we will have 1 0 0 0, and we again do the same thing that we did in the case of NAND gate. I will first draw the OR gate, this was the OR gate. Two switches are A and B, and we want the complement of the OR. This is OR and we want the complement of the OR, so we are going to remove the two switches from this position and we will have a new position for them. We will have a new position for them. It will look something like this. A, B, and this is the output Y. This circuit is the complement of OR. Fine. So this is all for this presentation. You can definitely find this circuit by using this truth table, and in the next presentation we are going to discuss the circuit for XOR and XNOR operations, and also we will solve few examples depending upon the switching circuits. So see you in the next presentation.